Today we're going to look at vector geometry in 3 dimensions. Now the addition of this third dimension actually doesn't change any of the calculations that we've done. We'll still use subtraction to find a vector between 2 points. We'll still use Pythagoras' theorem to find the magnitude of a vector. We just have to basically remember that we've got this third dimension, and obviously where previously we had i's and j's, we now have this extra one, k, that represents the z dimension. So we'll get into this question. We have A, B, C, D are points 2, minus 5, minus 8, 1, minus 7, minus 3, and 0, 15, minus 10, and 2, 19, minus 20. Now we're being asked to find A, B, and D, C, and given our answers in this form. So we know from previously where we've been working on vectors between 2 points. If we want to find the vector A, B, we find it by saying we're going to take the vector OB and we're going to subtract OA. It's the old thing of A to B equals the vector B minus the vector A, using the triangle. So all we need to do is write these coordinates in terms of their position vectors, and we're off and running. So AB is given by OB, which is just the position vector of this coordinate here. Now the position vector I'm going to write as a column vector just to make life a little bit easier. So we've got AB is 1, minus 7, minus 3, like that, minus the column vector for OA, which is 2, minus 5, minus 8. And then we just use subtraction to find our vector AB. 1, minus 2, minus 1, minus 7, minus 5 is 2, minus 2, and minus 3 minus 8 is 5. So our vector AB is minus 1, minus 2, and 5. Next, to find our vector DC, we're going to do exactly the same thing. D to C is OC minus OD. And we just take our vectors from the coordinates that we're given. So OC is going to be this one here, 0, 15, minus 10. And we're going to subtract OD, which is 2, 19, minus 20. That will give us our vector DC. So we've got 0, minus 2, 15, minus 19, minus 4, minus 10, minus 20 is 10. And there we have it. We've been asked to give our answers in a specific form, so we need to rewrite both of those column vectors in terms of i's, j's, and k's. So here, AB then is minus I plus, it would be plus minus 2, wouldn't it? So we've got minus 2j plus 5k. Okay, so this is I, this is j, and this is k. DC then going to be minus 2i minus 4j plus 10k. So now we're off and running, because the next part of the question says show that the lines AB and DC are parallel and that DC equals to AB. Now that's kind of, we can see it hopefully from the question. You know, if we look at these vectors, AB, the I component is minus 1, and in DC it's minus 2. In AB, the j component is minus 2, and in DC it's minus 4. And subsequently, therefore, the k component is 5 here, and it's 10 there. So we can literally see it from the vectors, all right? And all I'm going to write for that is, you know, we've shown that. All we have to just basically say is 1, minus 1, minus 2, 5 multiplied by 2 gives us minus 2, minus 4, 10. Therefore, DC is 2AB. Okay, that's all we've got to do for that last one. So then it says describe the quadrilateral. So this is where we think back to what we know about quadrilaterals from secondary school. What we've got here is 4 coordinates. We have lines AB and DC parallel. And so what we've got is a situation. So AB and DC are also different lengths from each other. And so that describes trapezium. Okay. 2 parallel sides, one is longer than the other, and it's a quadrilateral. So those are the basic questions for 3D vector geometry, and we're going to get into some more interesting ones just now. So here we have, what we're told, P, Q, R, and S are the points here, and they form a parallelogram. So P, Q, R, and S, and find the coordinates of this point S. We're going to use vectors to do that. So now we need to just remember what we know about parallelograms. We've got a pair of parallel sides here, and we've also got a pair of parallel sides here. Now I'm just going to focus on these two, PQ and SR, and I'm going to say that for this parallelogram to be truly a parallelogram, PQ has to be equal to SR. And by that I mean it has to have exactly the same direction to make it parallel, and they have to have the same magnitude. So they literally have to be the same vector. So the reason I chose PQ is because I can now work out what PQ is using my coordinates. So PQ, very similar to the last question, we're going to do OQ minus OP. Remember, it's always the second minus the first. So we write OQ as a column vector, 7 minus 7 minus 7. And then we're going to take away OP, which is this one here, 4 minus 9 minus 3. So PQ, our vector, is 7 minus 4, 3, minus 7, minus 9 is going to be 2, minus 7, minus 3 is minus 4. So that's our vector, okay? Now we know then that SR has to be the same. So therefore SR equals 3, 2, minus 4. It has to be. Now SR can also be written as OR minus OS, the position vector of R, take away the position vector of S. And we have the position vector of R. So I don't know why they put minus 0 there, but it is just a 0. So we've got the position vector of R. So let's put in what we know. 3, 2, minus 4, that's SR. OR is 8 minus 2, 0. And OS is just something we don't know. So what I'm going to put in here is an X, Y, and a Z just to represent the 3 components that we don't know. Now all we've got is 3 equations. Because if we look at our I component, 3 equals 8 minus X. So we've got 3 equals 8 minus X, which means that X equals 5. We've also got that 2 equals minus 2 minus Y, which means that Y is going to be minus 4. And for a third equation, we have minus 4 equals 0 minus Z, and that means that Z is equal to 4. So that means that our position vector of OS, which is what we're working out, is X, which is 5, Y, which is minus 4, and Z, which is 4. So that means that the coordinates of S are 5, minus 4, 4. So again, just to recap quickly, that was just bringing together the properties of a parallelogram. Using position vectors, using the fact that we had 2 parallel sides of identical length, we could just set up a simple vector equation to work out what our missing point was. On to the third example. The third example is very similar to one that we looked at in 2D vectors, where we had to find, or we had to prove that some diagonals bisect each other. Now, like I said back when we did that question, if we're interested in the diagonals of a shape, we should write those diagonals as vectors before we start. So here we have this cuboid, O, A, B, C, D, E, F, G. Quite a lot of points, obviously. We've got A, B, and C vectors identified on the page, and they are the position vectors of A, B, and C. Prove that the diagonals bisect each other. So I'm going to start by describing the diagonals first. So how would I use a vector journey to get from O to E? Well, I'd go from O to B first. I'd then go from B to F, and then I'd go from F to E. And because I'm going on that journey, I'm simply adding those vectors together. So OB, straightforward, is vector B. BF isn't labeled on the diagram, but this is a cuboid. So BF is completely parallel to OC, and it has the same length. So it is the vector C. And then similarly, FE isn't labeled on the diagram, but it is the same length and the same direction as the vector A. So that's my first diagonal. My second diagonal is BG. So how would I get from B across to G? Well, let's see. We can go in many different ways, but I should go BF, so up to F, and then let's go F to E, and then let's go E to G. Okay? You could go in many different ways, but that's one way of doing it. So BF, we saw before, was the vector C. FE, we saw before, is the vector A. Now EG, that's the same length as the vector B, but it's going in the opposite direction. All right, so we have minus B over here. So those are our two diagonals, and that's our starting point. So what we're going to imagine now is that there is some intersection point. All right, and we're going to say that these diagonals will intersect at P. And we're going to do exactly as we did before, and we're going to work out the position vector of OP, firstly using this diagonal, and secondly using this diagonal. And what we're going to do is work out that they are actually, in fact, bisecting each other. So let's think, how do we get from O to P using our diagonal OE? Well, straightforward really. We've got OP is just going to be a half of, or sorry, not a half, we're trying to prove it's a half, but it's going to be lambda, our unknown, of OE. Okay? So that's using the first diagonal from O to E. It's just going to be some fraction of the line O to E. Quite simple. The second way of doing it using the diagonal from B to G is a little bit more complicated because we still start from O because it's the vector OP. So we have to get from O to P using the diagonal BG. So the first thing we're going to do is go OB first. And then we're going to go plus some fraction of BG. Now remember, we use lambda almost like for our first unknown vectors, and we use mu for our second unknown. So here we have two ways of describing OP, using one diagonal and using the other diagonal. So let's get that written down in terms of lowercase vectors. We've got lambda multiplied by b plus c plus a. And for OP here, we've got b plus mu multiplied by c plus a minus b. Okay, just taking the results from before. And now what we do, we expand brackets, we collect like terms, and we compare coefficients. So OP is lambda b plus lambda c plus lambda a. And over here, OP is b plus mu c plus mu a minus mu b. Now for this one here, we can tidy this up a little bit. We can say we've got b multiplied by 1 minus mu. Okay, so b minus mu b factorizes to this, plus our mu c plus our mu a. So now we need to equate our coefficients, right? Really, but we're going to just basically say that there has to be the same number of a's in this equation as there is in this equation. There has to be the same number of c's. There has to be the same number of b's. And what you can see from that is, well, we can see that mu is lambda, right? So lambda here is equal to mu here, same for C, right? And we're going to call that equation 1. And we can also see that lambda b has to be equal to 1 minus mu times b. Okay, that's equation 2. So again, just look at that. That's this number of a's equals this number of a's, this number of c's equals this number of c's, and then this number of b's equals this number of b's, and that's the really important one. Okay. So now to solve, I'm going to sub 1 into 2. Okay, lambda equals mu. That gives us mu equals 1 minus mu, which gives us 2 mu is 1, gives us mu is a half, and then we sub into equation 1, and we say that lambda is a half. Now, because we said that mu and lambda were, for example, the fraction of the diagonal, so here it's lambda multiplied by OE, our diagonal. For here, it's mu multiplied by BG, which is our diagonal. We've therefore proven. So this proves that the diagonals BG and OE bisect each other. Now, it's a tricky question. That's about as tricky as they get, but there's a process. Okay, let's just quickly look back at the process. Any question involving diagonals, write the diagonals as vectors first. That's what you do. What are those diagonals? Because then you can work with them. If they're going to intersect at a point, you can describe the intersection in 2 different ways, one using each of the 2 diagonals. And if you just remember that you're not supposed to know, for example, where they intersect, how far along each line they intersect, you can use lambda and mu as your unknowns. And then it always comes down to comparing your coefficients. Okay, so compare your A's, compare your B's, compare your C's. And then simultaneous equations gets you your answer. So, thank you very much, everybody. See you in a bit.